right then. The thing says we're live. That must mean we're live. Hey guys, what's going on? Memes here. Yes, this was not a normally scheduled broadcast, but as of last night, I noticed something. Something had come out recently from the CMS collaboration, basically CERN's compact muon solenoid, aka the CMS collaboration, which shout out to the entire group because congratulations, y'all. You won the breakthrough prize. Well deserved, in my opinion. Uh, and actually, going into the good work that the CMS collaboration has been doing, they recently released something yesterday, or at least I first came to actually notice it last night via the dumpster fire that is Twitter. So let's go to it right now. We're going to do a little bit of a shorter thing because I'm technically in Vegas right now. I'm going to go to WrestleMania in a couple hours. I know. Oh, woe is me. But let's go over here right now. Okay. So this was posted last evening, or yesterday afternoon, technically. And as we can see, it's from the CMS publications here. I know, such an engaging name. And this is something that I feel a lot of people may kind of glance over and they're like, okay, whatever. So basically, they've done further analysis of the data that they've collected over the number of past runs at the Large Hadron Collider, in particular, the CMS experiment itself. Okay. And basically, they're measuring the mass along with the width of the Higgs boson. Today, we're going to be focusing specifically on the mass of the Higgs boson. Why? Well, because they actually had some results that got me pretty excited. So we'll get into it here. As we can see, they have the combined measurements here. You see all this stuff here. Here's the thing. I'm not a trained particle physicist. I don't know what all this stuff means, full disclosure. But what I do notice is some of these things where you start going through and hold on, I'll get to it in a second. And then they actually have the prediction. Okay. Okay. So as of now, the current estimated mass of the Higgs boson has been revised. And according to the CMS collaboration now, the estimated mass of the Higgs boson, aka the God particle, is 125.38 giga-electron volts, effectively divided by like c squared, because if you're going to get a mass, but that's its mass energy equivalence. Okay. I know, I'm just showing a tweet here. Who cares? Okay, let's actually get into something a little bit deeper here. So let's actually, okay, so let's actually go to the publication itself. So this should be linked down there in the doobly-doo below. Feel free to check it out yourself. I mean, you can totally trust me if you want, but please verify. Trust but verify. I feel like somebody said that once. So we'll just read through the abstract real quick. And this came out about a week or so ago. So this is the combined measurements and interpretations of the Higgs boson production decay at root of S equals 13 TeV from the CMS collaboration. All right. As we can see here, the combined measurements of Higgs boson production decay rates are presented. I think that's supposed to be analysis included. Our analyses included use proton-to-proton collision data recorded by the CMS experiment at, as we saw, root of S equals 13 TeV from 2016 to 2018, correspond to an integrated luminosity of 138 femtobars to the -1 power, aka the inverse of that. So that's a measure of luminosity, not because it says luminosity right there. Okay, so it goes through, they're going through the decay rates and everything here, and they're going through the production mode. And again, the Higgs boson is a difficult thing to measure because you're not necessarily measuring the Higgs boson itself. You're measuring the lack of something, and then you're trying to recreate from those photons. Very difficult process. Like, to do this is literally, to me, magic. So as we can see here, the best fit inclusive signal yield is measured to be, so it's about 1.014 within the standard model prediction, and we've got our error bars over here, plus 0.055 or minus 0.053 times the standard model expectation. All right. That yields a Higgs boson mass of 125.38 GeV. Okay, so listen. This really shouldn't mean anything to most anybody unless you've probably been paying attention or are a particle physicist. Okay, so that's the mass energy equivalent of what it is currently believed, according to this research, that the mass of the Higgs boson should be approximate. Okay, so you see additional results are provided for the decay and as well as the other decay channels and everything. Okay, that's great. Why am I talking about this? Okay, so since we're at there, and again, I'm going to put forth a conjecture, and since we're conjecturing, let's conjecture ahead, shall we? Professor Wolfram, take us
Although
away.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
All right. So why am I even talking about this? It's like, all right, there's some numbers there, the new release, very slightly different because the last updated CMS measurement was about 125.35 GeV. Okay. So it went up slightly by like 0.03 GeV. Why is this important? This is important, I claim, because it does appear that there seems to be a relationship between the mass of the Higgs boson, the Planck mass, and the magnitude of Hbar, aka Planck's reduced constant. When you take Planck's constant and you divide it by 2 pi, basically a circle or a rotation there. And it seems to be tuned to that. Why do I say this? Okay, number one, if you just go into Wolfram Alpha and you naively put in this expression here, so you can literally just type or click. I got the thing linked in the doobly-doo below, at least on YouTube. So we've got the Higgs mass divided by the Planck mass. And one of the things you'll hear about, you'll hear something about the hierarchy problem or whatnot. And the hierarchy problem, it's kind of, if you listen to or read Matt Strassler's book, Waves on an Impossible Sea, he says when they say the hierarchy problem, that's basically from a human perspective, because they're talking about something, I believe they use the term naturalness, in that it was more expected by a lot of what our intuition is that the mass of the Higgs boson should actually be around the magnitude of the Planck mass. It's not, because if you just do this, if you just divide the Higgs mass into the Planck mass, if it was about the same, it would be close to 1. It's not. It's a heck of a lot smaller than the Planck mass, about 10 to the minus 17 smaller. Very small. Okay. Now, if we take, for instance, on Mindscape, Professor Sean Carroll had Dr. Cicerati on at one point. She happens to work in the field of particle physics. And one of the things that she expressed was that it isn't necessarily the mass of the Higgs related to the Planck mass, but it's actually the square of that. So we take the good doctor at a word, let's square it. Okay. So we get this here. So we get an even bigger number. Okay. Now, again, most folks, it shouldn't mean a dang thing to. However, if you're not a good physicist, because good physicists just set Hbar to 1 and they're done with it and they move on. Okay. Now, if you're a bad person pretending to be a physicist like me, and you've gone down enough Wolfram holes, you'll notice that this exponential power, along with these first 3 digits, seem quite familiar. Why is that? Because it happens to be the first 3 digits and exponential power of Hbar itself. We get that 1.05 times 10 to the minus 34 joule seconds. Now note the unit of action here. This is units of action, which is energy times time. That's correct, right? Hold on. Yes, energy times time. Because if this was energy, that would be time would be to the -2, because mass times length squared divided by time squared. This length and time, if those were both, if this was the same and that was -2, this would just be E equals mc squared, because c squared is length divided by time. Waka waka. All right. So the reason why this new result is interesting is because if you take this, okay, and hypothetically, let's say the Higgs mass was just not a random thing, and there was actually some reason for it to have its smaller mass that it does. Okay. So I'll claim that the mass of the Higgs is tuned to the Higgs mass divided by the Planck mass, all squared should be equal to the magnitude of h bar. Okay. Those were a bunch of words. Let's actually just go through it real quick. We're not going to bloviate. We're not going to go for a full hour because, one, I don't have the time, and number two, we're just going over, and I don't need a bloviate, so let's stop bloviating. Okay. So hypothetically, if we have the Higgs mass, and we've got it to about 3 significant digits. Now, this result, we have 5 significant digits, and there's going to be some error in there as well. But if we have the Planck mass, I'm putting in its energy equivalent here, just to come out in the same units, giga electron volts. Okay. So hypothetically, if we were to take the Planck energy, which would be the Planck mass times c squared, and we were to solve for x, if we were to conjecture that the mass of the Higgs boson should be tuned to this expression, and this expression is just, we have h bar divided by joule second. Okay. Why? Because the joule second is, joule is energy. That's our unit of energy. It's actually tuned to c squared. And then you multiply it by seconds. That will give you the units of action. So we take our elementary unit of action and we divide it by the reference unit of action. We get this number here, 1.055 times 10 to the minus 34. And again, this is actually rounding here, so let's note that. But let's go with this intuition right now. Okay. So if we go back and we were to make the claim that this x that we're solving for, because that's just going to be a variable, that if this conjectured mass of the Higgs boson divided by the Planck mass or Planck energy in the appropriate units, this whole expression squared should be equal to the magnitude of h bar, or h bar divided by its reference of action, the unit of action, the joule second. Okay. So if we put this in, it goes through, Wolfram Alpha does the computation and everything, and what do we get? So we're solving for giga electron volts. Oh, wait a second. Okay, so it's giving us a number of answers, and note, there are some negative because I'm not taking the absolute value in the first part. Maybe that's significant, maybe it doesn't matter, but we have 125.38. We're solving for GeV. Wait a second, 125.38 GeV. 125.38 GeV. Huh. That's interesting. Why is it that these new results seem to have pretty dang good agreement with what we're solving for here? If we set it tuned to h bar, we're getting out right about the same magnitude. To be fair, it's not precisely that, because if we actually go back, go back to just h bar itself. We just, we'll just do H bar. We want all the known digits, and we have H bar is actually defined at 10 significant digits now. And we used to have 12 significant digits, but the last two had kind of a large error. So when we were undergoing the SI redefinition and basically setting the definitions of SI and updating and everything, they just lopped off the last two digits. So as you can see here, this is, I think, like 9 digits. And then this is just estimated because I think it goes to about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the 7 should be the last digit. So if we just take that, take off the digits, put a little star there. All right, we got this many Joule seconds. Then we're going to divide it by Joule seconds. Give us a dimensionless number. So it's basically giving us the magnitude of H bar in a dimensionless form, okay, aka the effective magnitude of the elementary unit of action, okay. So now if we take all this, we go back to our other expression, okay. So let's actually put that in there, okay. Where that should give us a little bit more of a precise number. Okay, it's still giving us the same because we need more. Let's do this. NIST Planck energy. Codata, physical constants, H bar, elementary natural unit of action. Okay, so we got that. So, oops, I went to the wrong one. We're looking for the Planck energy. Okay. All right, so let's take the Planck energy too. And again, we have a little bit of error here. So that's about 1.2 times 10 to the 19 giga-electron volt. Okay, so all we're going to do is in here, space, and then that's times 10 raised to the 19 GeV. All right. So now we have additional information. So rather than just rounding there, it has, well, we have 1, 2, 3, 4, 5, 6, 7 significant digits there. We have 10 significant digits here. Let's solve and see what we get. Okay. So this is where we get the expression that I have in the doobly-doo on YouTube, that 125.376 giga-electron volts. And there's actually an error of 2 in the last digit here. So maybe that could be a 4. Maybe that could be an 8. That is awfully close to that 125.38 giga-electron volts, my friend. So it's quite interesting. So I'm sorry, I missed it, folks in the chat. Let's say hello to folks. Welcome, K-Show. Good to see you. Good to see you. Thank you all for joining. We're just getting ready to wrap up here. I just wanted to do this little thing because I got all excited last night. Just because, no, not only because finally got to Vegas after car breaking down for like the 3rd time or something. And oh God, it's a heck of a story. But yes, welcome, Grizz. Good to see you, my friend. Yes, all about H bar. I feel like I could come up with a song, but I feel like it's not going to come out quite as well as we should. Well, we get Charlie. Yeah, I talk to Charlie once in a while on Discord. We have some fascinating conversations around there. We got Poindexter joining. Thank you, my friend. Let's see. I think we're in the. Let's see what Charlie's saying. Charlie is saying that looks like the luminescence. The luminescence ether is back into play. People start getting about zero energy. Listen, I can't say what it is. Space-time medium, some superfluidic thing, space-time itself, but no ether. Kind of like that kid's book, but no elephants. I don't like what you call it, as long as it has a better description and it actually helps us figure out what's better going on. But that's my particular take on that thing. So, but as of now, again, shout out and congratulations to everybody at the CMS Collaboration. Y'all deserve the Breakthrough Prize. I'm totally biased on that because also your result happened to agree with one of my little pet conjectures here. So of course I'm going to be biased there, but I think we should be open and honest about our bias as best we can. Why? Because well, that's science. We're supposed to be looking for truth, not just things that make us happy. I say that as somebody that's talking about something that happens to make me happy because I'm like, that's really close to what we had there. So, but that's that's all I really got. Well, Poindexter. Here's the thing: a proper question is one of the big things because I learned from Thad that Einstein is attributed. I can't say that he said this because I wasn't there, but when Professor Einstein was asked about you have 1 hour to solve a problem in order to like save the world from destruction or something, how would you go about solving that problem? Professor paused and he's like, I would take 55 minutes to formulate the proper question and then spend 5 minutes answering that question because the appropriate question is very important. And this is something that I think a lot of good physicists might actually miss. Because if you listen back to Sean Carroll, most good physicists might miss this because he's like, if you ask me what the value of Hbar is, like, I don't know, because good physicists set Hbar to 1. I'm not a good physicist. I'm a dude on the internet pretending to be a physicist or claiming to do some different stuff and things and very simple person. I'm like, oh, let me look at this. Oh, I just happen to be pretty good at remembering the first couple of digits and exponential powers. That's all I really got. And I just happened to notice that. And then I'm like, all right, do the naive Wolfram calculation. All right, plug in some more digits of what's actually listed to our best hard won measurements that have taken millennia and countless people over the years working hard to get these measurements. I'm going to assume we're doing something right. I just happen to notice, oh, this seems to be about the magnitude of Hbar. And if future high precision measurements, because we're going to need more precision measurements before we can make that claim that there is something there. But at least in the direction we're going right now, it's starting to look like there might be a little bit more there than initially thought. So just something to be aware of. Perhaps we should pay attention to these things. And yeah, that's all we really got. Uh, yeah. Oh, I thank you, Charlie. It's listen. Ultimately, I break it down to there's a lot of different topics and everything that I don't know. So I just kind of chunk it as there's some stuff, doing some things. I might not know what the stuff is. I might not know the things that we're doing, but I just try to simplify it the best way I can so I can try to figure out better what might be going on or hopefully happen to spark an idea in some young person or some other person out there in the field that maybe they just needed this little extra just perspective or something to help them make the next great breakthrough so we as humanity can level up because I think that's the personal goal, or at least for me it is. So hey, thank you all for watching. Take care of yourselves. It's a crazy world out there, but take care of yourself.